Okay, so we're going to talk about thermodynamics in chemistry. Text box. Chemical thermodynamics. Again, it's a scary word, but there's no reason to be scared of it. So thermodynamics really just means the movement of energy in the form of heat. Okay? Thermodynamics just means the movement of energy in the form of heat. And when we put it in chemistry, it's as applied to chemical reactions. Ding dong. Bye, Robbie. Okay. So, chemical thermodynamics, and we are going to talk about a couple of different topics. Let's get some fire on here, shall we? And I'm not going to draw it. I'm actually going to get an image, you know. Fire. Maybe not the best one. Let's do, there you go. Let's just do a mountainside burning, shall we? That seems appropriate. Somebody sent me a fantastic meme for extra credit this past week. It was a toy set. It was like my first fireplace or something, like first fire set or something like that. It's like this toddler with these logs and a little like rubber rock ring that they can put. Anyway, I don't even know.
You talk about the gadget one that's like my first like fire starter.
Yeah, my first fire starter set or something like that. Anyway, the meme that they sent me was that there was a picture underneath it of a guy doing finger guns, and it was like combustion reactions. It was really good. Anyway, I thought it was funny. I laughed because I'm a nerd. By the way, I love your memes. They're fantastic. They truly sustain me. Okay, so the movement of energy in the form of heat is applied to chemical reactions. So there are two main categories of reactions and how they do heatness stuff. Okay? Those types of reactions are, as we discussed last week, and if you're watching the video and you don't know what I'm talking about, stay tuned for a video on a pretty cool reaction. Anyway, exothermic reactions. Okay, so an exothermic reaction is a reaction that releases energy. Okay, chemical reaction that releases energy as heat. Okay, specifically as heat, because there are some reactions that release energy, but they only release it as light. Okay, so for instance, or they release it more as light than as heat. So for instance, during the wishbox assembly, when I put a unadvisedly large piece of sodium in the water and it exploded, it did create heat, but it also created a lot of light in that reaction. Okay, so that was an exothermic reaction, but I would say that it was a lot of light being released in that reaction. Okay, so an exothermic reaction is one that creates heat as a product of the reaction. So when we write a chemical equation that is exothermic, we can do it like this. Okay, so the classic example, of course, is one that we've done a bunch. CH4 plus O2, and you know the rest, right? Goes into CO2. and H2O. H2O. Okay? Because this is an exothermic reaction, we are going to put plus heat as a product of this reaction. Okay? So this right here is going to be added to the end of our reaction because the heat goes out of the reaction, right? It is a product of burning methane. We light some methane on fire in an oxygen atmosphere. It makes carbon dioxide and water and heat, okay? So that's an exothermic reaction and how we write an exothermic reaction as a chemical equation. The other type of thermodynamic reactions in chemistry are the opposite of exothermic, and those are endothermic. Thermic reactions. And we'll make this a little bit longer here. Okay. An endothermic reaction is a reaction that doesn't release but consumes heat. Consumes. Okay? And I guess we should put, I apologize, chemical or physical. I apologize. These can be, oh gosh, that's ugly. How about that? That's better. Okay. A reaction, and again, this can be chemical or physical. What is the difference between those two again? What's the difference between a chemical reaction and a physical reaction? Yeah. Right, yeah. A physical reaction can easily be reversed generally, right? And oftentimes physical reactions are something like changing states, right? So going from a frozen state, a solid state, to a liquid state, that's a physical reaction, right? And these different reactions can consume heat in a way that the heat is not a product, but rather a reactant, okay? So, for instance, if we were going to do, so there's a reaction, we'll use this as an example. I'll need to write kind of small here, is C6H12O6 H12O6. Does anyone recognize that? Maybe from biology? It's glucose. Yep. Photosynthesis makes glucose, right? So this is glucose. When you do glucose plus water, okay, plus heat, remember heat is the reactant in this case, you get hydrogen, H2 plus carbon dioxide. Okay, so this is an endothermic reaction. It consumes heat. So in the reaction that we did last time, we put the potassium chlorate and the sugar in the crucible, right? And then we added a little bit of sulfuric acid. That was just as a, well, we'll talk about that in just a little bit, just to get the reaction started, okay? And the potassium chlorate and the sugar burned really hot, right? And your crucible went from about 20 degrees Celsius to about 200 degrees Celsius in a matter of a few seconds, right? That was releasing a lot of energy, okay? These reactions don't make things hotter, they make things colder, okay? They absorb the energy around them, they suck the life force out of the air or the energy in the table or whatever, and so they make things colder. Remember that when we're talking about heat or cold, sometimes when you touch like a cold surface, it can feel like your hand is being permeated by cold, right? Like the cold is going into you. When in reality, the heat is leaving your fingers. So the energy is not going, you are not getting negative energy. What you're doing is you're sending energy out. That surface is actually pulling heat out of you. So that is why we use the term thermodynamics. Thermo meaning temperature or heat. Dynamic meaning movement. So the movement of heat, right? So endothermic versus exothermic. Any questions about those two different types of reactions? It's pretty straightforward. Okay. So that's a little bit of a introduction there. Let's talk about a couple of other things with chemical thermodynamics, okay? So sometimes sometimes a reaction needs a little bit of heat to just get started, and then it can sustain itself, okay? So this is a little bit actually what we used with the sulfuric acid in the last lab. We're going to talk about catalysts. Catalysts. Make this bigger here. Has anyone heard this term before, catalyst? Yeah? So a catalyst, or catalysts, I guess I should, we'll keep it plural. Any energy or compound that starts a reaction. Okay? After which the reaction is self-sustaining. Yeah. After which the reaction is self-sustaining. Sustaining. Okay? So a catalyst, oftentimes we use catalysts like fire. Okay? So for instance, when you're burning a log, okay? What do you need to get a fire started? Like if you want to burn a log, how do you start burning it? Yeah. You light it on fire, okay, but what does that mean? Yeah, you can use the toddler toy kit called My First Fire Starter. Yeah, you can do that. You can use a stick, yeah, you can do that. What we need is we need to add in some heat, right? Is burning a log an endothermic reaction? What do we think? Does it need to consume heat in order to keep on going? Or does it release the heat? Yeah. Emma. Right. It doesn't need the heat to continue. It just needs it to start it. Okay. So when you have your lighter or your match or whatever, the catalyst for your fire is that match. Because after which that flame is self-sustaining. That is a chemical reaction, right? We're breaking down a hydrocarbon in the form of cellulose mostly in wood, reacting with oxygen, making water and carbon dioxide. Okay? When that happens, that's self-sustaining. That's just going to keep on going. Okay? In the case of our reaction of potassium chromate, not chromate, chlorate, plus, oh, that's not what I wanted, plus sugar. We use the catalyst of sulfuric acid. Okay, the reaction sustained itself. It didn't need more sulfuric acid. It was just there to get the reaction started. Okay. Who's seen those like ice packs that you boil and then you pull them out and then you like press a button or something like that, and then it freezes and becomes cold? That is an endothermic reaction that is actually, the catalyst is that little button. It's actually a small, like almost kind of like battery kind of a thing. Yeah, it becomes cold because it's absorbing energy out of the reaction. So you boil it to add energy in. So it's adding the energy in, and then you press that little button or whatever, and then that causes the reaction to go through the ice pack or whatever, thus completing the reaction. Okay? So you added the heat by boiling it. That was an endothermic reaction. You're adding in heat, and then you use the catalyst of pressing that button, which I think releases a small electric charge as the catalyst to start the reaction. That's pretty cool stuff, right? So it stores the energy when you boil it, and then what you do is you consume all of that energy when you start the little, you press the button. There's hot versions of that as well, yeah. Those are just chemical reactions. In fact, actually, I don't think those are chemical reactions. They're actually, are they chemical? They might be physical reactions. They are reversible. So they are probably physical reactions. I don't know exactly what's going on in those, actually. I don't know the chemical compounds in there. But yeah, okay? So chemical reactions started by catalysts, all right? And what we can see here, so for instance, we're going to draw a graph because I love myself some graphs, okay? So that's a really good x-axis, time. And then here we're going to do energy. Okay? And we're going to do this in energy, anyway. Yeah, E is energy, T is time, okay? What happens, so there's a couple of different ways of doing a catalyzation of a reaction, okay? A lot of reactions, let's use our fire log situation again. A lot of reactions, the energy curve looks like this. Okay? The energy curve looks like that, all right? There's a lot of chemical potential energy in the log, okay? So we're gonna label this as chemical potential energy, CPE. So in your notes, write that fully out, but you know, I don't want to write it out in my drawing because, you know. All right, CPE, chemical potential energy. And when we get to this point, the universe loves bringing things down, including my mental state. Okay? The universe loves bringing things down, especially in terms of energy. Nature does not like a high energy state. It wants to bring the energy state down. Okay? But in order to get the thing to roll down the hill, you have to first push up. Okay? CPE, chemical potential energy. Chemical potential energy. All right? Well, nature wants to bring this energy down, but the problem is we have to get this energy up before it will come down. And this, we're going to change our color here because, you know, might as well. This is where the catalyst comes in. Okay? Catalyst. Right. And in this case, this is a thermal catalyst. Thermal. Okay? In this case, we're going to do it the hard way. We're going to push the ball up the slope, and then it will just fall down on its own. Okay? In this case, this is lighting your stove or lighting a wood, log. That's the word I was looking for. It's a very difficult three-letter word. Log, right? And as soon as we get it to this point, as soon as we get to the energy here, the chemical potential energy takes over and we just coast down the rest of the way, okay? So the catalyst, in this case, is a thermal catalyst that adds in the energy required to start this reaction, okay? Questions? All right. Now, what we're going to do is we're going to draw another graph. Hopefully my x-axis is better this time. Oh yes, much better. Thank you. I know. Applause. I accept applause as thanks. Okay. And no one claps. Thanks. Yeah. I'm here literally all the time. Okay. Again, we're going to do energy and time because time is the x-axis for every graph ever, essentially. And we're going to do a reaction here, all right, where we have a lot of chemical potential energy here again. And, all right. In this case, however, what we're going to do is we're not going to use a thermal catalyst. We are going to use a chemical catalyst. A chemical catalyst doesn't add the energy that we need. What it does is it reduces what is called the activation energy, okay? So this little hill top for our chemical potential energy, this is called the activation energy, and because I can't write, I will type. What's it called again? Oh yes, activation. Activation energy. There we go. And it's exactly what you think it is. It's the energy needed to start the reaction. In this case, we're going to use a chemical catalyst. And instead of adding the energy in, we are simply going to reduce the activation energy so it just starts anyway. This is what we did with the sulfuric acid in potassium chlorate and sugar. We added the chemical catalyst, and the catalyst simply reduced the activation energy to where the reaction just starts.
Wait, so it doesn't actually like starting, it just makes the ball start the reaction?
Yes. It makes it so that the reaction can begin just at its ground state of energy.
So it makes it more reactive.
It makes it more reactive, essentially, yeah. It makes it so that you don't have to add in any thermal energy, okay? And remember, our energy is in the form of heat, okay? Thermal. Thermal energy, heat energy. That's why we're talking about thermodynamics, right? That's a very small L. Let's try that again. There we go. Catalyst. And this one is what type again? It's a chemical catalyst. I know, the graph did look nice before the writing, but so be it. Catalyst. Yeah, it's bad. Get over it. All right. Chemical catalyst. All right. I'm not muted, right? Okay, good. So that would have been bad. they just see writing. There's no talking at all. Okay. Yeah. And they wouldn't have heard any of my jokes, which is just so depressing. You know, I follow a YouTuber that he talks about stuff while he draws, and it's like he like draws anime and like, you know, birds and animals and stuff, but he's talking about completely unrelated topics like current events and stuff. Yeah. Anyway, so yeah, I could do that, I guess. I could just start drawing random things that have nothing to do with the lesson. or I could share a different screen so you all are seeing like me do graphs and things that are actually pertinent, but the other one is just me like typing random things or pulling up pictures that are completely unrelated. Here's a rubber duck. All right. Okay, questions about exothermic reactions, endothermic reactions, or catalysts? No? Okay. That is where I'm going to end the video for today. Look for the other video to be uploaded about exothermic reactions as an example about an experiment. Okay,